Hi everyone, my name is Janina Reuter. This is a talk about the generalization of the Euclidean algorithm for faster lattice-based computation. This is joint work with my supervisor, Klein. First of all, what is a lattice? A lattice is the set of points that we get by all integral combinations of the generating vectors a1 to an. For example, if we have generating vectors a1, a2, and a3, then of course a1 plus a2 is in the lattice, but also, for example, 2 times a3, so 1 times a3, 2 times a3, this point is in the lattice, as well as in negative combinations, for example, minus a2 or minus 2 times a2 is in the lattice. And the first thing you probably learn about lattices is that every lattice has a basis. So the lattice a1 to an, independent of the number n of generating vectors, always has a basis with at most d many vectors. So there is always b1 to bd that also generate the same lattice as a1 to an. And this talk is now about finding, with an algorithm, finding a lattice basis with d many vectors if given n many vectors as input. So I already mentioned that we claim that this is a generalization of the Euclidean algorithm. So let me first set the Euclidean algorithm to compare this with. We have given two numbers, s and t and z, and we want to compute the greatest common divisor of s and t. We have two operations, the modulo operations of s modulo t and the exchange operation, which then continues the same modulo operations, but now with t and the remainder r. Our algorithm now does something quite similar. We are given a matrix B and a vector A, and we want to compute the lattice of B together with A. So in some sense, we want to incorporate A into the lattice B. The modulo operation now operates on vectors, so we compute the modulo of A modulo the matrix B. This operation I will define in a second, and we get a remaining vector R. The exchange operation now exchanges A with any basis vector bi. There's just one limit I will also discuss later, and then this bi is exchanged with the remaining vector R. Now, in order to define the modulo operation, let's look at the fundamental parallelepiped of the matrix. If we have matrix B, the fundamental parallelepiped is just the image of the unit cube under B. So it's this parallelepiped of B. For the modulo operation, we look at two properties. We first have the volume of the parallelepiped is just the same as the absolute value of the determinant of B, as well as this is the same as the number of integral points in the parallelepiped. So the number of integral points in this parallelepiped is just the determinant and the volume as well. And as second, the space Rd can be partitioned into parallelepipeds. We use this property as follows. If we have a vector A and we get x as the solution of bx equals a, then we define the modulo operation of a modulo b as a minus b times x rounded down to the next integer component-wise. Visually, this is as follows. We have, for example, b1 and b2, and a vector A. Vector A lies somewhere in the space in some parallelepiped for B1 and B2. And then the origin of the parallelepiped is just B times X rounded down to the next integer. And the modulo is the vector that we get from the origin of the parallelepiped in which A lays to A. So this is the modulo vector. Regarding our algorithm now, we have that the remaining vector, of course, can be displayed as A minus B times B inverse A rounded down to the next integer. This is just X from the previous slide. And we terminate when A is in the lattice of B. Remember, the Euclidean algorithm actually terminates when the remaining value is 0. We here have the same, because when A is in the lattice of B, then this vector is actually integral. And if it's integral, the rounding does actually nothing. And with A minus, well, B times B inverse does nothing. So A minus A is just 0. So we also terminate when the remaining vector is 0. And if we terminate, then the correctness is actually shown pretty easily, because B together with A, the lattice of this, is the same as the lattice of B together with R. This is very easily to see, as R is just an integral combination of A and the vectors of B, and A also is an integral combination of R together with vectors of B. Now, for the bit complexity, we need to see how fast does this terminate. For this, let's look at how we can measure the progress that we do with the modulo and the exchange operation. We have B1 and B2 as before, and now C is just the remaining vector from the origin to in the respective parallelepiped. If we look at the new parallelepiped, then we can see that its volume, or the determinant, is by Cramer's rule just the determinant of the old basis times x2. And since x2 is just something fractional smaller than 1, we of course do terminate, but we also want to terminate fast. So we need to use some degrees of freedom that we have. For example, we are not set to exchange B2. We could also exchange B1. So we exchange B1 and look at B2 and BC and C, what the parallelepiped now is that we get. And that is just x1 times the old determinant. So by this, we can always choose the beta xi to increase the determinant, but this doesn't give us a good guarantee yet. We need one more degree of freedom, which is that we are not set to use the origin, but we could also start with any corner of the parallelepiped. So it is also valid to do as the new basis B1 and B2 minus C. So we get then that the new determinant of B prime is 1 minus x2 times the old determinant. With this and with this vector or this vector at choice, we can always ensure that our determinant decreases by 1/2 in each step. So we have at most logarithm of determinant many iterations. Let's look at an example. We have B1, B2, and A. A lies in some parallelepiped. We have some remaining vector R and exchange B1 with R. Then we have R and B2 as the new exchanged lattice basis, and we have the vector B1 which we want to incorporate. It is in the parallelepiped of B2 and R1. In this parallelepiped, we get R2 as the new remaining vector. We exchange B2 with R2, and our new basis is R1 and R2, and we see that B2 actually is already in the lattice of R1 and R2, so we are finished. And we found, with R1 and R2, we found the A basis for this lattice. Now, in order to get our running time improvement, we need to do even more optimization. We need to use the degrees of freedom that we have in a clever way to have even less number of iterations. Especially, we need D at most. For this, we again look at the parallelepiped. So we have B1 and B2, and we have some vector C which we want to incorporate. And our goal is to use implicitly or explicitly the Euclidean algorithm of one dimensions as a subroutine. And we use it on the translate. So a translate of B1 is just B1 shifted to the next integral points. So this is the first translate of B1, this is the second, and so on. And if we now look at our algorithm and we pivot always by the same vector in each step, so we pivot with B2 always, then we get the following. In the first step, we get a B2 prime, and we exchange with C, we get a B2 prime. Then we exchange again. We get a vector G on the first translate, and we do it again. And if we look at G and B1, then we see that the projected vector now lies on the subspace of B1. We can also see that G as the a vector on the first translate is actually a good choice for our basis. Why is that so? Well, if we have G, we can continue without G with all the other vectors on the subspace that is spanned by the remaining B vector, so with B1 in this case, and C prime. This is because since there are no vectors, no integral points between the zeroth translate and the first translate, all of the points on the other translates can be found with the vector G. This does not need to be on translate 1 in general. This can be on this is in general the translate which is the GCD of the translates of B2 and C. And with this we can get to any translate which is reachable by the lattice. Okay, so how does our algorithm look like now? We have a matrix A1 to AN as our input, and we want to find a basis, a D times D basis of the lattice spanned by these vectors. We first find independent set of vectors B1 to BD as our starting basis from the original vectors, and all the remaining vectors we collect in a matrix C. In order to improve our running time, we solve the linear system just once, the linear system of B times X equals C. We solve it once, and then we iterate over all of the dimensions D. For this, we choose a row index L of X with maximum fractionality. For correctness, we actually can choose any row index L, but for the running time, I will explain in just a second that we need some condition on the row that we will choose. Then we determine the translate T and Ti of the vectors BL and Cs. And for each of these, we compute the GCD translate with the respective vectors and how we can represent the GCD vector on the GCD translate and how we can represent the projected vectors of Cj on the subspace of the B without BL. Yeah. And then at the end we have a representation of the GCD translate vector on the GCD translate for all of the translates. And we can remember this as one representation for one of the final basis vectors. At the end, we can then compute the basis S by B times Y. Complexity-wise, we only have a for loop up to D. However, in this for loop, we need to deal with potentially large numbers in the solutions for Z and X. Therefore, for this, we need this notion of fractionality. Fractionality we define in some sense as what is the minimal multiplication factor that we need, lambda, in order to scale the index I solution vectors to an integral. So in other words, how fractional can the solutions of the linear system be at index I? This is the fractionality of B at index I. And we actually have a theorem on this. So for a given matrix B, the number of points in the parallelepipeds, the number of integral points in this parallelepiped is just the fractionality of B for some index j, this can be any index j that we can pivot, times the number of integral points in the subspace of B without the jth vector. In this example, let's look at it. We have a subspace for B1 And on the subspace for B1, there are 3 points, integral points, this, and this. And we can see that this holds for every translate, actually. So in this translate, there are also 3 points, as well as here, and so on. So the total number of points is just the number of points for each of the translates, so for the subspace especially, times the number of translate that there are for the parallelepiped. We can do this for B1, but we can also do it for B2. Now, if we look at the subspace for B2, then there's only one integral point in the subspace, and also on every of the translates, there's just one integral point. So, in other words, there are many more translates in this direction with each 1 point than we have in this direction. This we can use in order to analyze the complexity of our algorithm, since if we look at the algorithm and we choose the maximum fractionality when choosing the index, then there cannot be many iterations where these numbers are large. Okay. Now, our result for the bit complexity is that the algorithm is bounded by the time that we need to solve the linear system at the beginning, so bx equals c, times this cubic factor, let's say. And roughly, we can bound the time to solve the linear system by this term approximately. In just a second, I will tell you how this number, where this number comes from. But first of all, let's compare it to previous work. So previously, lattice basis computation was done by 2 ways. The first is variance of the Hermite normal form, which the current fastest algorithm is by Laban and Storjohann, which is actually older than me, and the running time is n times d to the matrix multiplication exponent times the logarithm of the largest entry of A. However, a major drawback of this approach is that in the Hermite normal form, the numbers can grow with the determinant of the lattice. So these can be theoretically, and also in practice, they can be exponentially large numbers in the output basis. The other approach is a variant of the LLL algorithm, which is slower, but it can improve the output size of the basis. Yeah, so in the LLL type algorithms, the size of the output basis is at most a factor of square root d times a. Now, our algorithm is actually a best of both worlds type of algorithm. Regarding both of the previously talked about algorithms, we can guarantee the same growth similar to the LLL variant, and also we can improve about the running time of the Laban and Storjohann algorithm for the HNF algorithm, where this exponent is actually approximately 0.12 smaller than the matrix multiplication exponent, and this isn't a coincidence because our more precisely stated complexity scales with a rectangular matrix multiplication exponent, which is omega k, and we can choose for our running time, we can choose any rectangular multiplication k. Especially, we can always choose k equal to 1, and then we get the rectangular matrix multiplication of for a d times d matrix and a d times d squared matrix of dimension. And then we get that omega 2 minus 1 is just the value that you've seen before. And if we compare it to omega, then it is the improvement by, as I said, roughly 0.12 in the exponent. Now, our algorithm, in fact, is quite easy to implement, and we wanted to see whether the practical performance also holds up with the theoretical performance. Therefore, there was a bachelor thesis by Josh Burgel, a bachelor student of Kim, who implemented our algorithm and compared the running time to the fastest practical implementation that we know of, which is in Sage, the Hermit normal form algorithm. And as you see, starting from about dimension 75, we can see that our algorithm is much, much faster than the Hermit normal form algorithm implemented in Sage. Okay, that it is for me. Thank you very much for your attention.